Okay, Assalamu alaikum. So today we are going to talk about image processing in the frequency domain. So in this part we are going to consider how the image is treated in the frequency domain, not in the spatial domain like we did in module number 2. So first of all, we need to know that any function that is periodically repeats itself can be expressed as the sum of sines or and cosines of different frequencies, each multiplied by a different coefficient. This is what we call the Fourier series. So even functions that are not periodic but whose area is under a finite curve can be also expressed as an integral of the sine and cosine multiplied by a weighted function, which is the Fourier transform. So in general, if you have the signal with different frequency and amplitude, as you can see here, if we combine all these signals, we can get something appearing like this. So you can see here that the frequency domain refers to the plane of two-dimensional discrete Fourier transforms of an image. So the purpose of the Fourier transform is to represent a signal as a linear combination of sinusoidal signals of various frequencies. So in order to understand the Fourier transform, let's go through the Fourier transform in one dimension. So the one-dimensional Fourier transform and its inverse are as follows. So if we have an image, if we have a signal which is f of x, the Fourier transform for that image is basically the integration from minus infinity to infinity to from minus infinity to infinity for f of x multiplied by e to the power minus j 2 pi ux dx. Now, j is basically the imaginary part. E to the power j theta is equal to cosine theta plus j sine theta. So the inverse Fourier transform, so if we want to get back our image, so we are going to do the f of x is equal to integration of minus infinity to f of u, which is the transformed image, e to the j 2 pi ux du. Okay, so this is the one-dimensional Fourier transform. This is the inverse Fourier transform. This is the two-dimensional Fourier transform. And this is the inverse two-dimensional Fourier transform for any particular pixel, which we have f of uv is equal to the integration from minus infinity to infinity, the integration from minus infinity to infinity to for f of xy, which is the pixel value at the point xy, e to the minus j2 pi, a to the minus j2 pi, and multiplied by ux plus uvy. Now, if we go back over here, this is e to j2 pi ux. Now, this means what? This is equal to cosine theta. Theta is 2 pi ux plus j sine 2 pi ux. Now we are going to apply the same over here, but this time, of course, dx by dy, but this time for u and v. Now, since we are talking about images, and most of the time images are discrete values, we are concerned mostly with the discrete value of an image. So the discrete value of an image, the Fourier transform for a discrete value is f of u 1 over m, where m is the number of pixels, sigma from x is equal to 0 to m minus 1, the summation of all the pixels. Okay, this is the number of pixels, 1 over the number of pixels, sigma from x equal to 0 to m minus 1 for f of x e to the j minus j 2 pi ux over m. And this is the inverse Fourier transform. Now, if we assume, for simplicity, f of u is equal to x of k, which is the Fourier transform, f of x is equal to x of n, so it's a small letter, it's the actual value, and the capital letter is the transform value. Let's see how it's done. So the discrete Fourier transform and the inverse discrete Fourier transform definitions can be expressed in a matrix form, which is interesting for us because if you have an image is basically represented as a matrix, and so we are going to discuss that in for details. So expanding the discrete Fourier transform with n equal to 4, n equal to 4, here m is equal to, which is m here, which is 4, okay, n, which is the number of rows, is equal to 4, we get x of 0, x of 1, x of 2, x of 3. These are from 0 to 4. This is the output. The input is x of 0, x of 1, x of 2, and x of 3. Now, the Fourier transform is basically E, this matrix is e to the minus j 2 pi over 4, j 2 pi over 4, let me clear this one, j minus j 2 pi over 4m is equal to 4 multiplied by m n 0, 0, 0, 1. So e to the power 0 is 1. So since 0 is multiplied by all these values, let me highlight them. Since 0 is multiplied by all these values, then these values will all equal to 1, as you see. Now, when we come to this value, e to the 2 pi over 4, okay, e to the 2 pi over 4. What is 2 pi over 4? It is pi over 2. So it is basically e to the minus j 2, pi over 4. This will equal to what? This will equal to cosine pi over 2, sorry, cosine pi over 2 minus j sine pi over 2. What is sine pi or cosine pi over 2 is equal to 0. Sine pi over 2 is equal to 1. So it will give you minus j. Let's check this one. If we check this one, this one over here, it is e to minus j, sorry, this one, e to the power minus j 2 pi over 4 multiplied by 1 multiplied by 2. So this is 2, 2, 4, 4 will equal to e to the power minus j pi. So this is cosine pi, okay, cosine pi minus j sine pi. What is cosine 180? It is minus 1. What is minus j? What is sine 280? It is 0. So it will give you minus 1. So like this, we can express all the values that we see over here. And then this is our values. Now we can multiply the row by the row and the column by the column to get our output. So using vector and matrix quantities, the discrete Fourier transform is given by these values, where x is the input vector. This is x is our input vector, and w is the transformation matrix, which is this matrix over here. Now, if we apply these signal for the inverse Fourier transform, the same, we will have the transformation by 1 over 8 multiplied by these values. We will get our values as you can see over here. Now, this is compared to this one is the conjugate. This is the conjugate of w, the conjugate of w. So an example, consider that our image has these values. x0 is equal to 3, x1 is equal to root 3, x2 is equal to 1, x3 is equal to minus root 3, is computed as follows. Now, we are going to compute it. Now, to find the value, we need to do the multiplication of the matrices. So we multiply the first row by the second the first row by the column, the second row by the column, third row by the column, the fourth row by the column. So 3 multiplied by 3 multiplied by 1 is 3, plus root 3 plus 1 minus root 3 will equal to 4. 3 multiplied by 1 is 3, minus 3j minus 3 minus j, we will end up with 2. We will end up with 2 minus 2j root 3, and so on. We get our values. So this is the output of the image. We can find the inverse Fourier transform for that image by doing this multiplications. So you should be familiar how we do the multiplications over here. Now, I will stop here for this part, and we will continue in the second part in the second video, inshallah.